Okay, thank you so much for joining this. This is the Exploratory online seminar number 29. We started this workshop, I think, a few weeks ago. This is the fourth episode of the entire thing. So this one is visualizing uncertainty. Okay, so just in case you don't know me, let me introduce myself. My name is Kan Nishida, CEO, co-founder at Exploratory. Beginning of 2016, I launched the Exploratory as a business and also the company to build a product called Exploratory with other three partners to democratize data science. Prior to that, I used to be working at Oracle, leading a team to build a data science related products, ranging from machine learning to data visualization to database and big data and so on. And then after that, I left, and then because last 5 years or so, I started seeing dramatic growth in data science technology and algorithms. But those are all happening in the open source world. So we wanted to bring that to outside and then to build up, best product in the data science by using all the technologies and algorithms available in the open source. So we call it the third wave, basically to bring this amazing capability into everybody's hand, regardless of your background, regardless of whether you can program or not. When we say data science, we mean usually you start with the questions, and then you want to access the data to answer the questions. But most of the data you access not in the format that you can visualize or analyze. So you want to do data wrangling to clean up the data, transform the data to the way you can visualize and analyze. And then you apply visualization technique to visualize so that your eyes can intuitively see the trends and the patterns from the data. But sometimes your eyes are limited, so that's where you want to bring in analytics capability or algorithms such as statistics and machine learning algorithms to find patterns in the data that your eyes might be missing. And then you go back and forth, any sequence, any order, and then eventually you find insights that helps to answer the questions. Then sometimes you're the only one who makes the decisions, then that's the end of the story. But most of the time, you work with other folks, like customers and partners and coworkers and so on. So you need to communicate the things that you find from the data. So the communication is also an important part of the data science workflow. And we build Exploratory to make these 5 things: data access, data wrangling, visualization, analytics, and communication, to be in a cohesive framework inside a modern and simple UI. So that's really the Exploratory is about. Okay, that's enough for myself and Exploratory introduction. So let's get into today's seminar. So Exploratory seminar number 29, Viz workshop part 4. This time we're going to cover the visualizing uncertainty. Okay, so let's say I have delivered this awesome presentation, right? About 10 people, 20 people, whatever. And then at the end, I ask the audience to give you a rate. So very bad is 1, very good is 5, 1, 2, 3, 4, 5. And then I got all people answered. And then I just kind of use the histogram to see how many people at 1, how many people at 2, how many people 5, and so on. And then I get the average of 3.6. So this time I consider my performance, so my presentation is rated as 3.6. And then I have done another awesome presentation the next day. And then I ask them, audience, to give a rate. And this time I got slightly different, the distributions. So, but average score is 3.4 based on all the rates people gave. And then next day I have done another presentation. And then again, I surveyed, and then I got answers back. And this times I got 3.3. So I got like first time 3.6 and the next time 3.4 and next time 3.3. Seems like it's downgrading, but nonetheless, same content, same type of talk, not much difference. And I still got the different scores, 3.3, 3.4, 3.6. Then like I ask question like, hey, which one like I should consider as my performance? Well, the thing is, in this world, the things are kind of random. So the numbers vary. It always has a variation. Sometimes even like the same contents and the same type of people, but still sometimes 3.4, sometimes 3.5. That's not surprising thing. That's where we live. And then also the average, we're talking about average score here. So the average is very sensitive. It can be influenced by extreme values, especially when the size is small. When I say size, it's meaning like number of the people in this particular case. So let's consider, for example, like I got like 7 people. And then like we're talking about age, and 20 years old, 22 years old to like 32 years old. And then like, we calculate the average. Here, like I say, mean is basically the average. And the 26 is the average or mean year. And then also just to give you a little bit more idea, it's like there's another concept called median, right? So median is the number that like you sort all the numbers from the smallest to the biggest, and then pick the center value. So that's the median. So this case happened to be mean and median the same. But then when I replace the 32 years old person at the most right hand side with 60 years person, a 60 years old person, then the mean change or average change. Now, like we're talking about, like average is 30 years old, as opposed to the median. Median doesn't change because it's always center value. So that's what I mean. When you have the smaller sample size, then the mean or the average can be influenced or can move. So, when you do let's say the survey, you're talking about, let's say 10 people or 20 people, and you happen to have the one person gives like a, too good score or too bad score for whatever the reason, might not have anything to do with your performance itself, then that skew the mean value. So now I have also delivered the same awesome presentation with different number of audience. Last time I did it 3 times, but I always like about like 15 to 20 people. This time, like I deliver in different locations. And then the first time I got about like 10 people or so. And then like I got like I calculated the average to be like 3.4. Next time I got bigger audience, maybe like let's say 20 or 30 people. And then I got average score at 3.5. And the next time I got even more, like let's say like 40 or 50 people or something, then average score 3.6. Again, number varies, 3.4, 3.5, 3.6. But also this time, the number of the people in the audience are different every time I do. Then I would take that, for example, this time, I got 3.6 with the biggest audience, right? More people. So I would take the number from the biggest crowd or audience more seriously because the outliers won't impact so much on the average. So let's say like if even like one person give me a score of just 1 or something like that for whatever the reason, but that if that's only one person, then that's not gonna impact on the mean value as much as it does with a small amount of people. So intuitively speaking here though, the bigger the data size is, the more trust we want to give. If you have like only 3 person compared to 30 person or 300, I would give more trust to the 300 group, right? So ideally, I want to give the presentation to as many audience as possible and get the survey result from them, right? Let's say like, I don't know, 1,000 or 100 1,000 or 1 million or whatever. However, but I've got a small group. Um, so, and this is what I got. And then this time I got like 3.6. Then here's the question. What I really want to know, oops. What I really want to know is like, I want to understand like my exact true performance score, right? Not just with this particular set of the people who randomly happen to be here. I want to see like how good, how bad my performance is. So what can we do? And in statistics world, we call these things special name. So the left-hand side, a lot of people or more potential, all the audience that potentially should come or can come to my presentation, can meaning like whoever like a fit to this particular subject or something. And then right-hand side, we call it sample in the statistics. But essentially, what that means is the data we have or like people actually came to my this presentation. Okay, so population and the sample. And then both of them can have the average score or mean. I'm gonna start using more like mean. So the population mean, let's call it like true mean. That's a true, like that's like real value. And then the right-hand side mean is a sample mean, or the happen to be, I mean like a mean, but it's a mean of the group we happen to have. Okay. So we have no way of knowing the true mean of all the potential audience, which is the left-hand side we had, because they didn't join the seminar for whatever the reason was. And it's impossible. It's just not going to happen to have every single people on the planet that fit to like my segment or something. Okay. And then, but we know the mean or score of this group, this particular presentation, like let's say like 10 people, 20 people, something like that, as 3.6. And that's the fact. I have that data. Then most likely though, then this sample mean of 3.6 is different from the true mean. But can we have a range around 3.6? Let's say like I have the 3.6 this time, but can we have a range from mean to, I mean, smaller size to the bigger number, assuming that true mean will reside within that range? Then if we can, then what would be that range? And then this is what we call the confidence interval. So different names in this world, but I'm gonna just use this as a confidence interval. Okay, so let's say like we have like sample mean this time, like my score is 3.6. Okay, and then we don't know what the true mean is, like my real score with potentially like all the people on the planet. Well, we don't know that. So what we want to do is like, can we have like some range? And let's call it like 95% confidence interval. And then we can have better feeling or like it's kind of weird to say the feeling in the statistics, but we can have a better sense of like, okay, might not be the 3.6, but could be 3.5 or maybe 3.7, 3.65, but probably should the true mean, so the real value should reside in this range. And then what is this 95% confidence interval then? Is the calculation wise, it's calculated based on the mean of this particular sample. So let's say 3.6. And the standard deviation also can be calculated with the data we have. Let's say like we have 20 people, and then like we can calculate the standard deviation, which is basically the root of the variance. Or like in an intuitive speaking, the standard deviation is the average of how the data varies from the mean. Okay, and then like, you also multiply root n, 1 divided by 1 root n. So that n here is a sample size. So let's say like I have 10 people, that n is a 10. If I have 20 people, then n can be 20. we can calculate from this. So, but what that means is, what this really like as a concept, what that means. So let's say like we have the population at the top, and then we take many samples. Let's think of it as like if I give the presentation, like not just one time, like let's imagine like I gave the presentation 100 times or many times, right? And then take the survey and then get the average, and then calculate the 95% confidence interval. Let's assume like we apply the mathematical formula and then calculated the 95% confidence interval. And each confidence interval can be different because each time the average difference, not only the average though, or mean though, but also the standard deviation can be different. Okay. And then 95% confidence interval means if I do 100 times of this presentation, then 95 out of the 100, the confidence interval of the 95 of the 100 should include the true mean. And that's really the 95% interval, confidence interval. That means sometimes even, let's say like I happen to have these like 20 people get the average and calculate the 95% confidence interval. Maybe the true mean might be outside of that 95% confidence interval range. But that the chance of that is 5 out of 100. So what that means, and then so we basically take the 20 people, get the average, and calculate 95% interval, confidence interval. So we happen to be looking at just one of those 100, which is kind of weird because we are not going to do like 100 times. We don't have to. We are just talking about like a mean and a 95% confidence interval. Why we do that? Because we want to estimate where the true mean and then true mean should resides. And this chart might be even easier. So this literally like we did 100 times. And then like the dot at the middle is the average. And then those line, kind of horizontal line, are that 95% confidence interval. And then the black line at the center is the true mean. However, we have to be careful. We don't know the true mean. That's the whole point that we actually draw this confidence interval. We never know because we can't test like every single people on the planet or every single potential customers or so on. So this is sort of like I just pretend like I estimated the true mean at the vertical black line. And then 100 lines, but like 95 out of the 100, the confidence interval should include the true mean. And 5 out of 100 doesn't include the true mean. Okay, so that's really the confidence interval. And then there are different variations. They say like 90% confidence interval or 99% confidence interval, but the concept is basically the same. Like if you want to go with, hey, you know what, not just 95 out of 100, I want to make sure 99 out of 100 should include the true mean, then you can actually you can do the calculation as well. I can change a little bit of parameter that in the formula the guy showed you. And then obviously the range will actually get longer to make sure 99 out of 100 always include the true mean. And if you go down, look at this, like 90% confidence interval, the range can be shorter because now like we can have a 10 out of 100 can miss the true mean. So it can be like range can be a little shorter. Okay. So having said that, I want to do like exercise, and I'm gonna just do kind of a demonstration. And after this class, and I'm gonna share the slide with you. And then you can take a look at the slide, and also you can download the data, and then do it by yourself as well. Okay, so to do this exercise, I'm gonna use this employee data. Okay, and then this data is each row is each employee. And it has other 27 attributes about the employee. Let's say again, how old are they? Attrition is like if they have left the company already or not, or which department they work at, how much money they are making, and so on. And then to import this data in here, you can actually go from here and the extension data, data catalog. When you go to the data catalog inside Exploratory, then you need to be online to access to it. And then there's the HR employee attrition. If you don't see it, you can actually search it. And then once you see HR employee attrition, then click on this import button. And that actually download the data from the server we host, like exploratory.io. And then you click on the save button. And I'm going to just give a name and then just download it and import it in Exploratory. Okay. So, and then now like we are looking at the summary view, and then when I go to the table view, same thing we are seeing, like each row is each employee. Okay. So now, the first thing we want to do here is a question of, oops. Let's compare the average monthly income between a male and female. Okay, and then we want to see like if there's a incomes or salary, there's a difference in the monthly income between a male and female, and then if there is, how that difference, how they differ. And the second question is, we want to see not only as a whole, but also want to find that difference between male and the female in each job group. We have, okay, so here we have the gender column, which is male and female. Looks like there are more male, more men than women. And the other thing we're talking about is here, monthly income. So monthly income ranges from $1,000 to $20,000. That's a huge difference. But there's that. And then the mean is $6,500. Okay. And then another thing, the second question we're going to cover is this job role. So there are like 9 job roles, unique value 9. And then such as sales executive, research scientist, laboratory technician, and so on. So we want to find, first, there's a difference in monthly income between the gender. And we want to find all kind of deep down in each job role. Okay, so to do, we can go to the chart view. And then we're going to use a chart called error bar. Let's pick this up. And this chart can be used to visualize this confidence interval. And then the uncertainty, this seminar is about uncertainty. Why we call it uncertainty? Because the monthly income is not just one single value. It has a variation from 1,000 to 20,000 or so. So we don't know like where that is. And then if you get the one single value, like me, let's say $6,500, but we don't know how that is representative. So there's uncertainty. So like how we're gonna visual, how should we understand it? And that's where the confidence interval comes. So if we give like this range, and then the real mean should reside in probably here, 95% chance. So that's what I mean by the visualizing uncertainty. So essentially, like we want to use a confidence interval, visualize the confidence interval. Okay. So now, like first thing first, we want to see the monthly income, the difference between monthly income by the gender. By the way, though, let's start with a bar chart. I think that first step is nothing special. Like I'm going to assign a gender at the x-axis, and the y-axis, I'm going to assign a monthly income. Default is sum, but at this time, we want to see mean or average. And then when we look at here, like when we compare, let's say the female is 6,600 and the male is 6,300. So it seems like when we focus on just the average, the female is making more. Okay, so but let's be careful. Like we're looking at just one single value, and then like how this one single value or the summarized value is representative. I don't know. So that's where like we want to actually bring in the error bar. Okay, and then you see this error bar, basically the bar chart, but at the top looks like a bar, like a black vertical bar. Um, so that is basically showing the 95% confidence interval. Okay, and let's focus on just the confidence interval part, not without this this box or the blue box. So you can do that by changing the marker to circle instead of bar. And then now we're just looking at the, those like a black bar. Now it's colored as a blue colors. Okay, so when we look at here, what that means, so like here, the female confidence, that mean is monthly income, $6,686. So that's the mean, right? And then that, we already know that by looking at the bar chart. We already know like females average is higher than the male. But the question is that difference is something meaningful, that's something important or not, right? So that's because when we say like 6,600, but it can be, maybe like 6,000, it can be like 8,000, can be like 7,000. We don't know because one single value doesn't represent the whole thing. And then, maybe this time, like we have like a 588 people or female. And I'm not sure, like if we had, like we got like this 1,470 employee. I'm not sure this is the entire company. It maybe like it's just like a part of the company, or like if we had like this like a 5,000 employee, like this income value might be different. So that's why like we give a confidence interval. In this case, the default is here range type. You can actually change it between standard error 95% in confidence interval or standard deviation and so on. But this time we're gonna stick with 95% confidence interval. Okay. By the way, though, just a comparison, like let's change to like let's say standard deviation. So standard deviation is sort of like average of the, how the data varies. So one standard deviation, and then to see here, it's a range of like about like 4,600. So like that's about like average, like when out of all people, it seems like this is a range that people differ from the average. But let's stick with the confidence interval here. Now, we can say by looking at the range, says 6,300 to $7,066. The true mean should reside within this range. So out of like sort of like 95 times out of 100, or that ratio. So that means we don't know the true means, but it should be, it can be 6,400, can be 6,800, but somewhere around here. And then let's take a look at male, like we have 6,380 is the mean, but can be 6,200, can be 6,600, somewhere in this range with a 95% confidence interval. So what this really means is that when we compare, right now, like we're comparing between the female and the male, we want to see like that salary difference is really meaningful, or we should spend more time to investigate further. But when we look at this, even though the average is different, but interval, confidence interval is very overlapping. So that means that this particular data set, the average is different. That doesn't mean there's a difference between a male and a female. We don't know. It might be, but this data looks like with this 95 confidence interval, because real mean or real average might be higher for the male, might be lower for the female. So it can be same. It can be even like a male can be higher. So we don't know. So this is actually really useful in the statistics when you want to compare. You know, think of it like when you start with a bar chart and then you find a difference, and you thought that difference is significant or like meaningful difference, and then you start investigating further. But then like, often happen is that difference might not be that of meaningful difference, then you ended up like just wasting the time. But when you look, use the error bar with a 95% confidence interval, it doesn't have to be 95%, by the way. But in here, as a convenience, I keep using 95% confidence interval. Then this kind of difference, you can tell like not much of the difference. So, maybe like you can, you want to spend your time in something else, or you want to spend some time for like maybe making sure the data is correct, or how the data is collected, or other things. Okay, so now the second question was, so at this point, we don't know there's much difference between the female and the male. The next question is, okay, but maybe we have 9 job roles. Let's say like, what are the job roles we have? Sales executive, research scientist, or your manager. Maybe some job role, there's a difference between a male and female, right? So that's something we want to see. So go back to the chart. And then this time, I'm gonna use this repeat by. Basically, I wanna repeat this chart as many as number of the job roles, 9 times basically. So here the repeat by, and I'm gonna change to the job roles. And then we are looking at that same error bar for each job role. So starting from healthcare representative and human resource and so on. And we see the similar trend here, which is not much difference between female and male, but some differences here, which is the last one, like we saw, like females still like in terms of the average, female is higher. But now, like I'm not seeing that. Like some of the jobs, like research director, the male is higher, and then other is pretty much the same. Not much, even the average is not that much of a difference. Um, And then with a 95% confidence interval, basically, when you look at, let's say, like healthcare representatives, there's not much difference. Human resource, there's not much difference. And then you see like not just a little bit of overlap, it's like a whole thing is just basically overlapping on each other. And only the difference I see is this research director. Research director, male is getting paid like 16,600, and then female is 15,000. This is the average. But now, including the 95% confidence interval, females highest potential is like 16,100. And then male is the lowest potential is like 15,860. So there's still like a little bit of overlap here. Let's just zoom in, a little bit of overlap. But the difference is sort of like much more looks significant than something like a healthcare representative. So there might be something in the research director that makes male is getting more paid. I don't know what's happening, but it looks like there's something more meaningful difference here as compared to all other job roles. We don't see much of a difference. So that's so that itself is very interesting insight at this point. Okay, so we are looking now so far. Okay, so that was a very quick introduction to error bar. So now we were looking at the monthly income, which is a numerical. And in the data analysis, I think I got the part one, like I dig into like what are the data types, because that's very important for not just data analysis, but also even for like visualizing the data. And there's a couple of different data types, right? So like one is a numerical, the other is a categorical and logical, and then there's a date and time and so on. So how about the categorical and logical? Okay, so what that means. So let's say the gender. So this is categorical. It's a character data type, right? And a male and a female. And then let's say like we observe how many men and women are in this organization. And then by counting them outside the office. So let's say like we are curious about like female and male ratio of this company, like more female, more male. It's just that we are not talking about monthly income or something. We just simply thinking about this ratio between these two categories. And at 5 p.m., like I was just outside counting, and there's one person, one man came out. So like, okay, like male is 100%. But of course, nobody thinks this company is like 100% male. So I waited for another 30 minutes, and then two women came out. And at this point, it's like, okay, it's like a male is 66%, and female is 33%. Um, is this right? Or actually, this number is wrong. So I'm gonna just quickly change this. I think this is opposite. Okay. The female is 66% and the male is 33%. And then I waited under 30 minutes, and then now like we have more male, 60% of the 5 people male. And then like waited and waited. And then more employee comes, and then like obviously like this ratio slightly change, but more employee I count, or like more employee I have, then this ratio start looking into the real ratio, right? So even though like I don't have like all the employee, but the more I have, that should be getting closer to that real ratio compared to like I had only like a 5 employee. Okay, so even with the categorical or logical is, can be like true or false. It's a special type of categorical. But even with categorical or logical, the variance, that ratio of male female, that's actually the the let's say like you have like 5 female and a 3 male kind of ratio. That variance and also the sample size, you have 10 employee or 100 employee, are important when we consider the difference among the categories. When we talk about, do we have more female or male? Like these two things are important. We have to be careful. Then and so therefore, this is the same thing. Like we talked about a confidence interval for like a numerical sense, but also even for this ratio, there is a way to calculate the 95% confidence interval. But the concept is basically the same, because once you calculate those 95% confidence interval, even for the ratio, then that true ratio, the real ratio, should reside within that range, 95 times out of 100 if we take the 100 samples, for example. So then let's take a look. So first, let's compare the ratio of the male and the female, and then compare it for job role. Basically, a very similar thing we just did. Okay, so here I'm gonna create a new chart, and then select the error bar. Same thing. We're gonna use the same chart in the same way. So we're gonna see, I'm gonna assign the gender here. So this time though, and then I'm gonna use a circle. Okay, so this time though, we are gonna do something slightly different. So y-axis, last time like I assigned this like a monthly income, and then the calculation was average, like mean. This time I'm focusing on just pure like number of employees. So like a number of rows is good. But then not mean, like this is a calculation time, it says mean, but I wanna see the ratio between those two, male and female. So here, when female says 40%, okay, and the male is 60%. So like both of them, when you add up, like become 100%. So there's that 60%, 40% difference. And then we want to know if that difference is like when you said 40%, maybe it just happened to be 40%. If you, waited another 30 minutes and then like you got more employee, maybe the ratio can change. So we want to give like 95% in confidence interval to be sure. Then, so that's the ratio. So like female can be from like 37.5 30.5% to 42.5%. And this range, same thing for the monthly income case too, regardless categorical or numerical, this range can be bigger when you have smaller sample size. And this range can be smaller when you have bigger sample size, meaning like here, like I have like a 588 number of roles said 588 employees. But if I had like, let's say 10 times, like 5,000, that range tend to usually goes down. But there's another element to influence this confidence interval range, which is the original data's variance. So that's also need to be considered. But typically, the number of the data, the size is the determining factor. Anyway, so we have that, and then we want to see like if there's any difference in each job role. So we're going to do the same thing. Repeat by, let's assign a job role. And then we can see, okay, for example, manufacturing director or like a manager seems like, for example, manager is a good example here. So like we see like more male than female, but including this confidence interval, the difference, like we can't really say that, hey, somehow like we have more males than the female in a manager, what's going on? If you compare only that ratio, the one number, you can say that. But when you include this 95% confidence interval, we can say, hey, you know what, it looks like, but we can't really conclude that way. We don't have that evidence. But for example, when you look at the healthcare representative, and then these two, including this range, not overlapping. So we can conclude that with this data, we can conclude, okay, so there's something going on here, like we tend to have more male than the female in the healthcare representative. Okay. So the point here is instead of just using the bar chart to see just one single number and then conclude as if like you find something significant, but most often when you use something like confidence interval to include the uncertainty, then then like sometimes the conclusion can be different. So I think that's a really interesting stuff. Okay, so the last one I want to do, this is actually the most important to me personally. I think more than this ratio, but I think it's another topic, which is the question of here. Okay. Okay, so the exercise, compare the ratio of attrition among the job roles. So what that means, we have this column called attrition in this data. So this indicates if it's true, that means this employee already left. The false means this employee is still at this company. So we want to see that what is the, how different in terms of this attrition among the job roles. You know, anything is fine, even like martial status, marital status, or job level, gender, anything is fine, but we're gonna use a job role this time. So my question here is that, let's say like sales executive. Is this job role tend to have more people leaving the company? Or maybe research scientist? Is this job tend to have more people tend to stay? So those are the questions that I wanna answer. So basically, like we're comparing again, this attrition is that something of my interest, not that monthly income, not this time, not the number of the employee. I want to see like a number of the ratio of the true or the ratio of the people who left the company. Okay. So to do first, let's say like if go to the chart, and then let's create a new chart. And then same thing, selecting an error bar. And then like I want to assign a job role to the x-axis. Okay, and then again, I'm interested in this time is a ratio. So we okay, and what we are looking at here, I'm going to switch to circle. And also another thing I want to do is I want to sort this bars. So I'm going to use a sort by to y-axis, then like higher to the lowest, highest to the lowest, from left to right. Okay, so at this point, what we are looking at is the job role. So like the number of employee right? And then the ratio of the employee among all the job roles. Okay, so but that's not what we are interested in. We were interested in attrition rate. Okay, so so that's what we want to see. And then like I created some chart here. So target is I want to do like attrition. So what we are looking at here though, this chart is, let's say like I just pick like 4 job roles out of nine. But let's say like we have like a 326 for sales executive and so on, right? Like there's a number of the employee. And then what I did, create an error bar, was basically calculate the ratio. So this is 22% is out of all people. There's a 22% of the people here in the sales executive, right? So that's what we are looking at this chart. But what we want to do next is eventually we want to see the attrition rate. But first step is, let's say that if we assign the y-axis to attrition, so what is going to happen is here is the drop down, and then the number of true, number of false. In this case, I'm interested in the people who left. So number of true. Okay. And then here, when we say like attrition ratio to 28%, this 28%, we have to be careful because this is calculated based on all the people who left. That's the denominator. And then out of that, and then like how many people left. So that's what we're seeing. So it's here, 57 people left in a sales executive, and then 47 people in research scientists left, and 5 people, and so on. And then combine all of them, and then out of them, and then what's the 57%? So 57% is out of all people who left. It's 40%. And next one is 33%, and so on. And that's what we are looking at. But that's not what we want to see. We want to see the attrition rates. And when we say the attrition rates, it's not like the number of the people who left in a sales executive out of all the people who left the company. We are talking about attrition rates is like what's the percentage of the people who left in the sales executive, what that means. Like this, right? So like let's say 57 people left and then 269 people who still stays in a sales executive. Then I want to see like what's the chance of the people who are leaving in this vertical way. And it turned out the 17%, 17.48% of the sales executive who left the company. Same thing for the research scientists. I want to see in this vertical way, like 16% of the research scientists who left the company. And I want to see this ratio of the or attrition rate or ratio of those who left the company is higher or lower comparing to other job roles. And then say, like, I want to see, hey, what job roles tend to have more people leave? Then, you know, I might be able to take some useful actions, right? So to do, go back in here. So this ratio calculation, so what would be the denominator is very important. Default is all, so that means number of true attrition. So combine all of them, and that's the denominator. But in this case, what I want to do the denominator is this vertical, so like sales representative. The number of the sales representative people are, is the denominator. So I can click on this all button, link, and the ratio by, I want to do like x-axis, not all true people. I want to see like x-axis, and then apply. And then now at this point, what I'm seeing here is, let's say like 39.76%. That is the ratio of the true, or ratio of the people who left out of all sales representative. And the same thing for laboratory technician, human resource, and so on. Okay, so that's a little bit tricky, the concept. Okay, when we talk about ratio, the denominator is important. So, and then here in this balloon or in this pop-up, you can see the ratio by x-axis. So x-axis meaning like the kind of a vertical way. And so it's only each categorical value. Okay, so now when we look at it here though, so sales representative, not just the ratio 40% is high, but including the 95% confidence interval, looks it's different. The difference seems to be significant compared to others. Only thing is the human resource, there's an overlapping part. So human resource and sales representative might be same or closer, but compared to others, even like laboratory technician, sales executive, and all the other job roles, sales representatives rate of attrition is pretty high. So there's something going on with this particular job role. Now, here in the middle, let's say like laboratory technician, human resource, and sales executive, seems like these are sort of like overlapping, especially like these 2 or 3. And then also the last 4, like on the right-hand side, research director, manager, healthcare representative, and then manufacturing director, these 4 seems to be overlapping. But we can think of it as like these 4 job roles seems to be same. But when you look at compared to other, these we can consider sort of like a lower attrition rate job roles or the group of the job roles. So we can see like there's 3 groups, seems like 3 or 4, and then based on the attrition rate, but not just attrition rate, but including the confidence interval, you can see the different trends and patterns start emerging. So that's the beauty of the confidence interval, because average or the mean can fool us because depends on the number of the people or the sample size, or depends on the extreme values, outliers. But including this confidence interval, we can see, we can basically have more information. And then based on that, like we can make informed, better decisions. Okay, so that's really the visualizing the uncertainty. We have more contents, and also to what's behind the 95% confidence interval logic. There is normal distribution or central limit theorem and so on. But we don't have enough time to go into that concept. So I'm gonna find some time later, maybe like next month or something, to focus on those more like statistics topic, which is actually fun. So that's all for today. And then the next seminar is next week, Wednesday next week. I'm gonna cover like data wrangling for data visualization. So we have been doing like visualizing the data. It's pretty much clean data, but in real world, it's not. That's not the case. So there's a lot of things you can do in the data wrangling, but I'm gonna pick like some of the very common challenges when you try to visualize data, because data is not in the form that you can visualize and getting insights. So I'm gonna just cover data wrangling piece the next session. Okay, and that's it. And if you have any questions, please let me know. Chat is open, or you can unmute and then raise your questions as well.